Hello, everybody. All right. So we're going to look at number 14 that one of the classes was looking at in class, and this is from section, I think, 5.4 of the optimization problems. And it's a tricky problem, and we didn't have enough time to address all of it in class, so we're going to look at it now. All right, so the idea is there's a boater out in the water. It's not a sailboat, but let's draw a sailboat. I love sailing. And the boat is 4 miles if it were to go straight to shore. And then there's a motel or a hotel or some rockin' um, disco event. So fun. So this is where we're going. And that's from the shore directly 6 miles. 6 miles. So the idea is we want to figure out, oh, and when we're on land, so let's just make sure that here's the water. This is water, and land is green. Here's our land. And what we want to do is we want to make sure that, or we want to create a situation where it's fastest for the boat to just go straight to the hotel. And we want to know if what is the minimum rate that the boat needs to travel so that that's the case. So we're looking for, so let R equals, well, let's go B. Let B equal the boat's speed. Okay, so we're going to ignore waves, we're going to ignore tides, we're going to ignore all sorts of things. So B is the boat speed, and then our walking speed is 3 miles per hour. I think that's our units. So it's 3 miles per hour. And so what we're going to do is we want to find B so that the best route is to go straight. Okay, so the idea, what we do is we say, okay, let's suppose that we go somewhere to shore. So we row somewhere to shore, and then from there we walk. So it's going to be some sort of combination of rowing and walking. And what we're going to do is we're going to make it so that it's all rowing. But for now, as we set up the problem, we're going to say we row some bit and we walk some bit. Well, one of the equations that we're going to need to use is the fact, if distance equals rate times time, we're looking to minimize time, so we're going to use a time equation, which is distance over rate. So if what we're going to do is we're going to say, let's let this distance here be y, in which case this is 6 minus y, and 6 minus y is the distance that we're walking. So the time that we're walking is 6 minus y over my rate walking, which is 3. And the distance so that's the distance the time walking. And then here's going to be our time rowing. I've got a really good friend from Rhode Island named Jimmy Underwood, who's a big rowboater, so he'd probably appreciate this problem. He appreciates most things. Anyway, so the time rowing, well, we need to have our distance rowing. Our distance rowing depends on where we go. So it's going to be y squared plus 4 squared. So our time rowing is y squared plus 16 over the rate that we row. And we don't know that, so that's our variable b. Okay, so now the idea is we want to minimize our time. We want to minimize this time equation. So whenever we want to minimize or maximize, we're going to take the derivative. dokie. So when we take the derivative, we're going to get t prime, so time prime, equals negative 1/3. So just to be clear, we're taking the derivative of time with respect to y. So how the time changes as we change where we land on shore. So the derivative of that first bit is just negative 1/3. The derivative of this, well, b is a constant. I know that we're going to try to figure out what b is, but it's an unknown constant. So the derivative of that other piece is going to be 1 over b, that's the constant, times, now we're going to need to use the chain rule, y squared plus 16 to the negative 1/2 times the derivative of the inside, which is 2y, and we're good there. Okay, so for our time to be a minimum, for this time to be a minimum, our derivative must be 0. So we say 0 equals negative 1/3. And I'm going to rewrite this a little bit so that it's 2y over b, my boat speed, times y squared plus 16 to the negative 1/2. Okay, now what this is the sort of kicker of the problem. This will find my y value that minimizes the time, but what we're going to do instead is what we want to do is we want to say we want to go straight to shore because it's more fun to row. So we want to row straight to shore. So we want to know what must this b value be? B value b. B b b b b b b b. What must this b value be so that we go straight to shore? And if we go straight to shore, then my y value would be 6. So the idea is we want to find the b that makes this a minimum when y is 6. So we're going to substitute 6 in for y. And that should have just been positive 1/2. Okay, so what we're doing is we're saying we want our minimum time. So minimum, we set our derivative equal to 0. And we want our minimum time to occur when y is 6 so that we're rowing straight to shore. So we're going to have plus 2 times 6 over b, which is what we're looking for. And I know b and 6 look similar, but whatever, deal with it. Times 6 squared plus 16 to the 1/2. All right, so now we've got this equation, and we need to solve it for b. And when we solve this equation for b, that's going to find out what's the minimum speed I need to row at so that I'm rowing straight to shore, and that minimizes my time. And so the whole idea of this was that we set y equal to 6, which implies that we're rowing straight to shore, because if y equals 6, then we're going straight to shore. All right, so now let's do the solving of this. So moving some things around, we get 1/3 equals 12 over b times, I think that's 52. Yeah, 52 to the 1/2. And then to solve that for b, we get b equals, so doing a little cross multiplication, we get b equals 36 over 52 to the 1/2. And what does that equal? I have no idea. We have 36 divided by the square root of 52, something about 5. Yeah, 4.99999. So we'll say 5. So what that there shows us is that as long as my B value is 5, and remember that B is my boat speed, as long as my boat speed is 5, then this will be, if my boat speed is 5, because we just solved for 5, then my derivative will equal 0 when my y value became 6. And I wanted to make my y value 6 because that meant that I was rowing straight to shore, or straight to the fun spot. All right, that's the solution. Hope it made sense. This is a hard problem. Thanks for watching. If you watch this, just so I know that you watched it, send me an email that says, I watched the video, exclamation point, exclamation point. And then I know you watched it.